Let's talk about capacitors. What is a capacitor? When you say capacitor, think rechargeable battery. Okay, it's not exactly that, but it kind of works similar way. So this is a typical capacitor. This is called parallel capacitor. So you have a couple of conducting plates with some distance away. The gap is called D, and this is generally super thin. Okay, and then you hook it up to a battery. And then you charge one side with a positive and the other side with a negative. So what's going on really in atomic level is that negative charge, see from here, negative charge from here will get attracted to this positive. So it starts traveling this way, right? And then from here, negative charge comes out of this because electrons are the ones that's really moving. And then it starts storing here. So you're charging this plate with a bunch of negatives because overloading with the electrons here. And then you are sucking it out of, because in a conductor, the electrons are free to move around. So that's what's going on. Conventionally, and this is a term for conventional current, before they figured any of this out, because Ben Franklin has figured out the electricity, they used to believe that it's really the positive charge that's moving here this way and that way. Right? They really thought that's why everything, all conventions are done with the positive charges moving. It's called conventional current, as if it's some positive charge moving from positive to negative side. But people later figured out that's really not the case. It's the electrons that's moving. So it's like opposite. But it's too late, and then we are stuck with this anyway. So when you say current, it's really the electrons moving in opposite direction. So you should know. Anyway, so capacitor is the device that stores the charge, and then later you can use it, just like rechargeable batteries, but it really does something else in the electronic circuit. Any conductor, right, separated by tiny little gap between the two, and so one can be charged positive, the other can be charged negative, right, through a battery, is a capacitor. Because you can still store positive charges here. And this is a not so smart way of doing it. This is a better way, because you want to close this gap as much as possible. And reason for that is, say we have a bunch of positive charges here, right? And a bunch of negative charges here. It gets more and more difficult to push the electrons here because they hate each other. And then it gets more and more difficult to pull the electrons out of these guys because they attract each other. You know what I'm saying? Or if you think like this, positive charges go in here and negative charges go in here is another way of thinking about it. But they hate each other, so they really don't like doing it. So that's what this potential difference, delta V, comes in. So battery, a certain amount of, think of it as a water pressure. It's pressuring these things to go in, and it gets harder and harder, right? But if you close these gaps, then they kind of like each other, right? So it gets a little bit easier if you make this gap smaller and smaller, but these are conductors, so you don't want to put it next to each other. You don't want this to touch. So there has to be a separation, but they want these guys to be as close as possible, and then they are more willing to accept any more charges coming in. So they usually put something like paper or like super thin material, which is called a dielectric that we'll get into at the end of this session. But it's like paper thin kind of gap is what realistically is the size of this gap. Okay, so we understand what the capacitor is. It's like momentarily storing charges. Okay, and it's been charged and drained each time and many times in alternating current circuit. Okay, so here is something called capacitance, the maximum capability of each capacitor. Because eventually, with a given amount of pressure, they are not going to accept any more charges to come in, and that's the maximum capability. That's called the capacitance, right? That makes sense, right? And that's defined this way: total amount of charge per the potential difference. And this, people call it voltage. conventionally in electronics. So voltage, delta V, potential difference, right? That why we learned it, and we know what potential is, right? And that is commonly known as voltage. Okay, now, so the total charge that can be stored divided by the potential difference, delta V. But when we say delta V, we have to be careful because the way we define delta V was like this, right? Which means it could be positive or negative depending on which this direction this line integral is being moving. So when we define it, we want to just define a simple term as like maximum you can store. So this is maximum charge divided by higher potential, high minus low. So even if you have a negative integral value, you always want to take the absolute value and put it in, big minus small. Otherwise, negative capacitance, that makes no sense, right? And this is a unit of capacitor, which is known as farad, after Faraday, I think. Okay, I think so. Farad is coulomb, the unit of the charge, divided by volt, after the Volta, the scientist who came up with the battery. So, which is the unit of the potential difference, voltage, okay? Now, let's calculate capacitance. So first, we have this isolate, wait, didn't I just say that there should be two conductors and now there's only one? We can use infinity. Let's say this represents infinity, right? As the other one, right? Potentially. So what does that look like? So we have a positively charged conductor, and then compare that to zero potential at infinity. So potential is equal to zero right there. You know what I'm saying? I will rewrite it like this. Potential at infinity is equal to zero. Okay? Now, we always calculate delta V, potential difference first. Do you remember the potential? So this is potential at radius R, all the way to the center, right? Minus at infinity is how we're supposed to do it. So because this is higher potential here and infinity is zero. So this is just, do you remember what this was? KQ over R after integration from last session, and this is zero. Good. Okay. Now, and then once we have that, then we can calculate the capacitance, which is the total charge divided by delta V. You get it? So Q divided by this. So we just have R over K. Good. Remember what this thingy from Gauss's law, which was 4 pi K? Yeah. Which really means that 1 over K is equal to 4 pi. Depending on how you want to leave your answer, this is just fine, but in case it's a multiple choice. So this is 4 pi epsilon 0 times R. How about that? We'll calculate this different way later, so keep this answer in mind. Okay? Now then, this is just to demonstrate it's possible with only one conductor. Okay, parallel capacitor, the one we had up here. Okay, this thingy, which is most common form of capacitor in the olden days until they come up with a cylindrical one. So say we have two plates like this. Okay, and then we'll charge one of them with positive, so these are positively charged. And then these are negatively charged with the same amount. Good? Now, so here's the symbol for the battery in ENM. This is positive side and this is negative side. It's just a symbol for the diagram, okay? Now, we didn't do this when we are doing the Gauss's law, so I like to practice this here. The Gaussian surface that I'm going to choose will look like this. Cylindrical that goes into this thingy, and it comes out to the other side. You get it? Okay, so I want this radius to be r and this length to be L. Okay, and then we are given a charge density of sigma, of course. Okay? When we say charge density sigma, in case, well, let's just put it down here. Sigma always is total charge divided by the area of this, the whole thing, area of this plate. Okay? Now, this is not exactly infinitely big, but if you're close enough, remember I told you this gap is paper thin. So if you're close enough, it kind of looks like infinity, so you have almost parallel electric field going across. Because here it's going to bend outward, but we're going to ignore that, just somewhere in the middle. Okay, so it's a very good approximation. Now, so we'll do Gauss's law, and then last time we saw, my pen is not working. It was like this for Gauss. We are only calculating the electric field of this plate. Let's say positively charged plate. Okay? So we have E dot dA, and that is equal to total charge inside, the key is inside this Gaussian surface over epsilon. Good? Okay. Now we split this into three different surfaces. So there's one in this way, one that way, and then lateral. You know what I'm saying? But this one and that one is identical size and shape, so we'll say two of this surface, that is base area, base of the cylinder, of E dot dA, plus one of these as lateral, how's that? Lateral area. Okay, of E dot dA. And that is still Q inside over epsilon. So far so good. Now let's look at the direction of these field. Field, let's say, what color should I use? Orange. Field is moving in parallel capacitors, parallel that in that direction, correct? So the only penetrate, and then the other side, it will go out like that, parallel to the plate. So the normal vector of this surface right here is perpendicular, right? So that is lined up with our electric field. Good. So the dot product, the cosine theta here will give you 1. And then here, your normal vector goes out onto the top, and that is perpendicular to the field, so that your dot product gives you 0. So this quantity becomes 0. Good. So when we do Gauss's law, we have to identify which integral is 0 and which one is 1. Of course, just for the sake of review, we always choose a Gaussian surface so that our surface is perpendicular to the field and parallel to the field, and that's it. And we don't do it any other way. Now, then, this thingy becomes 2E dA is equal to Q inside, right? Over epsilon. But then this is constant, so we can take it outside. And then you have just the integral of S of base. Good? So far so good? Do you understand this much? Now, then this thingy is just the lateral area of the cylinder now, isn't it? So what's the lateral area of the cylinder? Somebody remind me? Not really. Not that. Oh, actually, you're right. I was wrong. This is the base area of that thing, so this is pi r squared. Good? And then we have two of them for this 2. Okay, lateral area here was 0. Integral. And then how much charge is inside this thing, and then amount of charge is stored in this disk right there, correct? So that's got to be the charge density times the area of that cross section. That is pi r squared, isn't it? So far so good? Okay then, now we over epsilon. Good? We divide. So our E is equal to pi r squares cancel from both sides. So we have sigma over 2 epsilon naught. Good? And then you, like, do you want to plug this in or not? It's judgment call, depending on what the answer key says. I'm going to show you how to plug it in later. We'll just keep it like this. But what is the total then? What is the total electric field? We just did it for one. So I have to decide what kind of electric field would this create. The second one is just going in, and this is going in like that, right? So they don't cancel. In between, they actually double up. And then out here, it cancels this thing coming up. So there will be a no field outside of these plates, and only field you see is in between. And then total electric field should be double of this, which is, so far so good? Okay, now we can calculate the potential difference. So having said that, and delta V, remember is this. Good. Let's say from A to B. And A to B, this is A and this is B. Let's just calculate it that direction. Okay, so this is A and this is B. Okay. Then since this direction, see, last time I showed you the opposite direction and there are three different negative signs and that was confusing. So what I always do is just go with the field and then we'll take the opposite for the potential energy if we have to, right? So that's easier. So that is now, this is just a distance d apart. Good. So isn't it just this thing times d? Good, because we have a constant, so we don't have to integrate. Wait, negative sign, eh? Negative sign, actually, we'll just keep it like that. And reason for that is that this is the direction is this whole thing. I take that back with a negative sign, because potential difference, if you go from A to B, it's got to be negative. It's decreasing. So real potential difference is really, if I want to calculate the potential energy or potential, I have to integrate the other direction. You know what I'm saying? But I didn't want to do that. For our purpose, it doesn't matter. Then we can calculate your capacitance, which is your Q divided by your delta V. I mean, absolute value if you want to, right? Okay, now here is where I want to substitute this value right here. Okay, so this sigma is Q over A, so what we have is Q D over epsilon and A. Good. The reason I want to substitute it is because I see Q here, so I want to cancel that Q. Okay, so dividing by this, so we will have epsilon A over D. Good. So what we can tell from here is capacitance is proportional to area and inversely proportional to the distance between them. And we kind of intuitively can tell, because if the plates are bigger, then you can store more charges in it for obvious reasons. And then I told you when this gap is smaller, then since they attract each other, so it's easier to push more charges in. So that makes sense, right? So this is the expression, capacitance of parallel capacitor, which happens to be the easiest kind. Good. Now, in modern days, really, cylindrical capacitor is really the more prominent ones, because these things are easier to manufacture. Okay, I have a picture later, but what they really do is they actually take a thin foil or something and then roll it with a paper in between. So you can put, with a limited space, you can put a lot of these things in. But let's just do this, okay? So we have charged the inside one, core one, with a Q positive, and then outside one with a negative Q. And then this radius of the inside core is A, and then outside is B. Okay, now first thing is, so this is a review of Gauss's law as well. we have to calculate the electric field, then integrate that to calculate the potential difference, and then we can calculate the capacitance. So we'll calculate the electric field. So the Gaussian surface, this whole thing is L, and what I'm going to do is really the infinitely long thing. It's not exactly infinitely long, but if you're in the middle and then only field you see is just parallel. One's coming out, inner core to outer core, and there won't be any. So that's what I'm trying to get at. So the Gaussian surface I'm going to put is, let's say this thingy inside looks like this, right? And then I'm going to put Gaussian surface like this in the middle of it. So this thing goes inside the surface like that, and then it sticks outside. You get it? So that's my Gaussian surface. Okay, that thingy, as always, has a radius of r. And then length, let's not use L because L is this entire thingy, so we'll say D, H, I'll call it H, because we used D before, so this is H. So that's my Gaussian surface. Then I can set up Gauss's law again. My pen works. So your surface, and then you have E dot dA is Q inside. I'm going to abbreviate that, but inside of this thingy. Good. Okay. Then this, let's break it up into three integrals again. So 2 of the base E dot dA plus 1 of the lateral. And that is Q over epsilon. So far so good? Now let's look at the direction of the field now. This electric field comes out like this, right? Oh, there's a picture. So these are all perpendicular to the lateral surface, but nothing is coming out to the top or bottom. Okay, so that gives you, this dot product is 0. And the other cosine theta will give you 1. Okay, then electric field becomes constant, so you can take it outside like this. So far so good? Now then we calculate the lateral area of the cylinder Gaussian surface, and that happens to be 2 pi r and then h. Good? Now we have to calculate the charge inside this thing. So let's define charge density, lambda, to be the total charge of the inside thingy divided by the length h. Good? This is a really good practice. Now, you get a feeling that this outside charge that does not really matter. Even if it's not there, we get exactly the same amount of electric field. So we have length density, lambda, times h would be the total charge inside the surface. Okay, then divide. So h is cancelled. So we have lambda over 2 pi epsilon, and then we'll just write 1 over r like that. Good? Wait. 2 pi. Wait, no, I was right? I think yeah, I'm right. Lambda over 2 pi, and then h cancels, so times 1 over r. Good? Okay. Now, this thing is 2 pi lambda. Remember this, right? 1 over epsilon is equal to 4 pi k, right? I'm going to substitute that in. So this thingy is lambda, and I'm going to put 4 pi k here over 2 pi, and 1 over r. That's prettier now, isn't it? So that this cancels, so we have 2 pi k. Did I say k and write my usual thing? 2 pi k, then lambda, then 1 over r. How's that? Oh, pi cancels. 2 k lambda times 1 over r. Good? Now, should we plug in, let's plug in this lambda. Okay, so what we have is 2k and then q over h times 1 over r. So first of it, okay. Now we'll take a limit. If you say as h approaches this entire length L, we expand it, right? Then this h becomes L, correct? So what we have is electric field will approach 2k q over L and then 1 over R. Good? Okay, so that's the entire potential difference of this. I mean, you could have put the Gaussian surface all the way up there and down there, but number one, we'd never finish this one when you're doing Gauss's law, so I wanted you to practice the infinitely long wire thing. And second, up here is kind of tricky because this field will actually curve like that on top, so it's like it creates complication. So I did not want to do that. But this is that's why it's like limit approaching this. So this is a very good approximation. Good. Then we can calculate delta V. Delta V, of course, is this from inside A position to B position. And once again, this should give us negative number, right? Because we are moving from higher potential to negative, lower potential. But it's so much easier not to care about the opposite direction, especially for our purpose. We just want the magnitude anyway, right? So negative, and this is the same direction, so dot product we can ignore and then E and then replace ds with dr instead of our parametric function. Now we plug this in for E. So taking constant outside, so we have 2kq over L, all of it is constant, and then A to B of 1 over R dr. Good? Okay. Then negative 2kq over L. Is this ln? Are we sure? Okay, only write down ln if you're sure. Negative 10-point deal. Plug it in. So 2ka over L ln B minus ln A. Why am I keeping absolute values? I guess they are positive numbers, right? So we can just put in anything. So it's like, right? Did I write A? Getting confused by my own handwriting, eh? So this is negative 2kq over, this is L, not Q. All of my letters look exactly same, don't they? And then you can say ln B over A. How's that? Good? Now, then we calculate the capacitance. Capacitance is Q over delta V, absolute value. So we knock out this negative sign, right? So what we have is L over 2k ln B over A. How's that? Good? In case you want to use the epsilon instead of k, remember 1 over k then is equal to 4 pi epsilon A. So once you put that in, then you will have 2 pi L here, right? and then, oh, epsilon, and then you have ln d over a. Okay? In your handbook, the answer key is wrong. In your handbook, you have this, ln a over b. This is wrong. I think that that mistake came from this. This is a negative sign, so instead of this minus that, that answer key probably switched the two. So have a over b, right? And then, oh yeah, you get rid of negative sign. No, that's still a negative number. Because a over b, ln, this is less than 1 if you put a over b. And then if you take ln, see, ln of a over b is still negative. So you still have to take the magnitude. Just because you got rid of negative sign does not mean it's a positive magnitude. You know what I'm saying? So it's like, don't do that. So this is a correct answer. So that answer key is wrong, so don't lose sleep over it. Okay? Okay. Now, the next one, we have spherical capacitor. But if we learned anything from this case, you remember this outside charge did not matter? So if we do the same thing, this outside charge would not matter, then our answer here should be the very first thing we did, just a spherical thing inside compared to infinity. Let's see if we really get that. So here, I'm going to put my Gaussian surface, of course, spherical one right here with a radius r. That way all of the field is perpendicular to my surface. Good. Okay, so then I set up this Gaussian surface, E dot dA is equal to Q over epsilon. Good. Do we need to, let's do it quickly since I started already. So this becomes E times surface area of this sphere, which is 4 pi r squared. And then this thing is capital Q, right? Over epsilon. Let me convert it to 4 pi k capital Q. How's that? So I'm still using this relationship. 1 over epsilon is equal to 4 pi k. Okay? Then divide, so my electric field is exactly the same as a point charge. 4 pi is cancelled, so we have kq over r squared. Good. Now, let's calculate delta V. So delta V is equal to E dot ds from A to B. Good. Okay. And that is negative this thingy. So taking kq outside, A to B of same direction as the r. So we have 1 over r squared and then dr. Okay, integrating that thing. So we have negative kq, and then this is r to the negative 1, therefore negative sign from A to B. Okay, use plumbing, professor. So this one, so 1 over A minus 1 over B. The reason I did not cancel this negative sign with that is I want this to be a positive quantity and not really deceive anybody, because A is smaller than B, so 1 over A is bigger than 1 over B. So this whole thing is positive and there's a negative sign because we are going from high potential to low potential in our integral. Good. Then our capacitance is Q over delta V. A little caution. Is it 2Q? Here's a Q, here's a Q. Is it 2Q or is it just 1Q? It depends on the definition, right? As you guys are right, it's 1Q. If we go back up here, remember here's a Q and here's a Q, and we call that just Q. when we define the capacitance, right? So literally there are two opposite charges, right? One positive, one negative. But if we think like this, then just one Q, right? So that's a little tricky. So don't be putting two Q because there are two of them. No, no, no. Capacitors come in pairs. Yes.
Wait, so when would you put 2Q?
Never.
Never.
That was the whole point, right? Because sometimes when you're doing this and you see Q here and you see Q there and going, is it 2Q? It could be confusing, right? I mean, if you're new to this, so I'm telling you never to put 2Q. Okay. So then Q divide by this, so that Q cancels. Okay? So we have, oh, by the way, take the absolute value of that thing. So we have common factor. I want to common factor this. KQ, I mean, you don't have to, but it looks prettier. AB here and then B minus A, and you can see that's definitely positive. You know what I'm saying? So we have AB and then over KQ and then B minus A. So this whole thing is positive when you knock this negative sign out. Of course it does. Like that. Good? Okay. So far so good?
Yeah, I have a question.
Yes.
In that picture, what's the like club thing?
Technically, as I copied it from the textbook, but technically this Gaussian surface could be anywhere.
Oh, that's supposed to be the Gaussian surface.
Yeah, but nobody really does that because then you have to do a surface integral. Yes?
Yeah, I sort of thought that it meant like just sort of like an imaginary cutout area that's
Oh, is that what it is? Maybe. You just inside sphere, outside sphere, but they just cut this thing out to show you the inside. Let's call that. That sounds so much better than, yeah. I had no idea. Okay. So far, so good. But just to show that this is the same answer as the first one, let's just do this. As B approaches infinity. Okay? Let me go back to this delta V, right? So if you take a limit of delta V as B approaches infinity, and then we'll use this expression, right? Then that becomes negative KQ just over A. You know what I'm saying? Because this thing dies. Then your capacitance is Q divided by this. Oh, not negative, absolute value of it. You know what I'm saying? So we have A over K, which was same thing, 4 pi epsilon A, which is exact same answer as our first one. Right? So this outside thingy does not really matter when you have this one inside, one outside. Okay? Okay, but people always put the outside shell because in order to charge this thing, it's so much easier to have one side connected to positive, one side to negative, and charge it that way than just charge inside thing and not outside. That itself is a headache. Okay, now, then if you have multiple capacitors, how do they add up? Okay, so let's get to that. I'm trying to do this in a rush so that I can finish it in one session. Okay, first one is parallel. Okay, this is reality. Now, abbreviation. These are the symbols. Capacitor is this, and battery, you see that in battery, one is shorter than the other. You don't have to really make this one thicker, but positive, negative side. Capacitors are same vertical lines. And then switches, if you need to put switches, they do it like this, open versus close. This is current is flowing, here current is not flowing. Okay, so let's just think intuitively. Is this same thing as just connecting this plate with that plate and this thing as that plate? You just put it together because remember capacitor, a parallel capacitor is proportional to the area of the plate. So you have double the area. So these things should just add, right? So intuitively, if you put it in parallel, this diagram is equivalent of just one capacitor with two of them added together. You would think, right? Let's see if I can do a semi-proof of that. See, capacitance is equal to Q over delta V, and delta V is a potential difference coming out of battery or power generator, okay? This thing tells you that your Q is equal to C times delta V, and you will use this a lot to find the total charge, okay? Now, then Q total is whatever you can store into this plus whatever you can store into this. They each store, they are like Q1 and Q2. Q1 and Q2 will be stored in each capacitor. Now, when you're thinking like this, those of you who are not familiar with the electric circuit, think of it as a water pressure. So you have a water pump draining. Let me draw that equivalent diagram here. So capacitor is equivalent to this, different water level, and then you are connecting this thing with some kind of pump. You know what I'm saying? So you're draining one and then you're putting into the other one so that it builds it. This side has higher water pressure, this side has lower water pressure. So you're literally sucking the electron out and or pushing positive charge here and then draining it from here. So these two wires from here and here have exactly the same potential, and these side have exactly the same potential because it's just free-flowing electrons. That makes sense to you? You have to be very comfortable with this analogy later. Okay, so we have this. Now, that means Q1 plus Q2, whatever the charge you can store in each capacitor, okay? These two capacitors. Now, that is, of course, according to this relationship, C1 delta V plus C2 delta V, correct? But I just said with the water analogy, delta potential is exactly same on this side and exactly same on that side. So potential difference between the two, wherever you measure it from here to here or here to here is exactly same. So these delta V's are really the same delta V. That means we can do C1, C2, common factor delta V. And this is your total capacitance, isn't it? Because that still looks like C times delta V, right? So that total capacitance is same as adding these two things. And that kind of makes sense because if you have two capacitors and you independently store amount of charges, total capacitance is put into. So that we expected. So likewise, if you have more than one, then you just add them up. The key is they have to be in parallel. See, I just emphasized the parallel, meaning what's coming next is series. Series meaning this kind of arrangement is called series. Now we have to think about this a little bit because the potential difference is not the same. When you say potential difference, delta V from here to here is not same thing as delta V from here to here. And if I say another delta V from here to here, in fact, if you add these two, it's exactly the same as that. Why would that be the case, right? We have to think like this first. Think water pressure, right? You're pushing water in here, right? So you're shoving positive charges in here. Those positive charges will attract the negative charges out of this plate. So whatever the positive charges that are here will be pushed out of it and will be stored here. Whatever's negative here will come over, so you're charging all of this to positive and all of this to negative. And that remaining positives are here. But then that will make these things negative. You know what I'm saying? So what ends up happening is, Here is the water pressure difference, potential drop between here and here. Potential, once again, is the difference between the two. So, and then there will be additional water pressure difference between here and this pipe and this pipe. So that makes sense to you that this total delta V is equal to this one plus that one, right? However, amount of charge that is stored, right, has to be the same between this one and that one. Because if I charge this thing with 4 positive charges that I saw, that'll attract 4 negative and chase 4 positive out here and then 4 negative. You know what I'm saying? Because they attraction repulsion relationship. So your charges are exactly the same and potential differences do add. Good? Okay, with that, once again, remember this. C is equal to Q over delta V, right? Now, from here, now I'm going to solve for delta V, which is equal to Q over C. The reason for that is because my potentials do add. Delta V total, here is delta V1 plus delta V2, isn't it? Okay, now I'm going to use this relationship. So this is Q over total capacitance that I'm trying to calculate of these two things together is equal to delta V, once again, is Q, same Q because amount of charge that is stored is exactly the same per each capacitor, over, and this is C1. And this is a Q over C2. How do you like that idea? Wait. You buy that this amount of charge here is same as amount of charge here. Is that the same thing as the entire charge? No, there's no way, right? Or is it? If you put a black box around this so you can only see as one capacitor, total charge you can store into that whole thingy, is it same as just whatever is stored in this one capacitor? Does it even make sense to you? Think like this diagram. I have 4 positive, 4 negative, right? 4 positive, 4 negative. So the total you can only see, think like this, is 4 positives here and 4 negatives here. And whatever's in the middle, they cancel each other. They are useless, aren't they? So in reality, you are seeing only 4 positives here and 4 negatives here. And that's it. That's all you can use when you drain this, because these two will go back to their own places and cancel. So effective amount of total charge in series combination is just same as Q. It's same as 1. You get it? So far with me? And then divide both sides by Q. And then you have this one weird relationship. This is not same thing as reciprocal, right? I mean, like, God, I hope you know that much. So algebra does not work like that. Okay? So if you have multiple of them, this is the bunch of total capacitance you can calculate. Right? You really get less than each one if you figure this thing out. There's a reason for that is just the complexity of the circuitry in electrical engineering not to store more charges. Okay, capacitors are not really, modern days at least, used to store charges. It's just, it does something inside the circuit. Okay, now let's take a little exercise. This is a diagram. Or okay, this is one of them. And we are supposed to calculate the total capacitance. The diagram, it's like you're only given this one diagram, but we have to think and evolve our thoughts, okay? So I'm gonna actually move it up and I'm going to sketch and then revise the diagram as we go, okay? So only thing you're given at the moment is and this side has this, and then, oops. So you're given this. Good. And then amount of is 4.0 microfarad. Actually, even microfarad is huge, so they use picofarad. But, and then this is 8.0, and this is 1.0, and this is 3.0. Okay? First thing you do is identify which is parallel. Well, this is parallel to this is parallel. So you just add these two, right? So we can replace this with you know what I'm saying? And then this, you can replace it with 6 microfarad then, because these two add. So you get rid of this, and this is how your brain thinks. This is 6.0 now. Oh, what was it? 2 and 6. Oh, this is 8. Good, 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 good. Now we have to add these things, right? So the total capacitance here, 1 over whatever, is 1 over 4 plus 1 over 4, which is 1 over 2. So that C total is equal to 2. You know what I'm saying? And then likewise here, total capacitance will be then 4. You with me? Well then, this thing now changes to just one capacitor with 2.0. And this thing changes to 4.0. So first was this picture that's given here, which evolved in your head to this, and that evolved into this, right? And then you add these two, so the total is just 6.0, which is this. So this is not just one diagram, but it's an evolution of diagrams. That's how you want to think in circuitry. And then later, if we throw in resistance, we'll be doing this a lot. Okay? Okay. Now the energy. If you're charging, when then you're storing energy, right? In rechargeable batteries, that is effectively storing energy. So how much energy can we store into capacitors then? Okay, remember, it was empty. So it takes 0 effort to push positive charge in. So if you put one positive charge in and one negative charge here, putting the next one, well, this one is not gonna like putting another one in, so they hate each other, right? So you have to do the first one took 0 work. Second one, like we are thinking as like electron by electron level. Second one, you have to do a little bit of work. The third one, these two both collective, oh, did I put positive here? These two collectively hate the third one coming in. So it gets harder and harder and harder as you store more charge in, right? So what ends up happening is this relationship. This is the amount of voltage you need to apply, the pressure you need to apply to shove more charges in, right? Wait, doesn't that look similar like potential energy of the spring? Yes, it is. Okay, remember, the work is your charge times your potential difference. Remember that? Okay, so what we want is that dW is equal to delta V times dQ. Little tiny bit of charge that you put in it. Now we can integrate from whatever 0 to, oh, the total charge Q. That makes sense to you? Okay, now, what is delta V? I mean, we kind of think it's a linear function, but what is delta V? We have to go back to the definition of this thing, right? So that tells you this delta V is equal to 1 over C Q, if you will. Right, so this is the slope of this line. Good? So we plug that in, so we take 1 over C outside, 0 to Q of the Q squared dQ. Q, let's put lowercase. Because a Q here is a line, so this is a Q, lowercase q right here, and capital Q is the total amount of charge that you're going to put in. That makes sense to you? So as you put 1, 2, 3 charges in, those are like lowercase q. So it gets more and more and more difficult. Good? Oh, then we can integrate this. Huh? Oh, no, it's not squared. Good? So 1 over c, and then you have 1/2 q squared a. So we have 1 over 2c, and then capital Q squared. How about that? Good? Okay. So this is the total energy that is stored in a capacitor. So let me summarize it here. So total energy stored in a capacitor is Q squared over 2C. However, remember that Q from here, Q is equal to C times delta VA, depending on what you're given. So substitute one of them, then you have QC delta V over 2C, and C's cancel, so you have Q delta V over C. Or you can, right? No? Q. Oh, no. Put, let's see, Q delta V. Yeah, over 2. If you substitute one more, then this is both C squared, right? C squared delta V squared over 2C from there. And then C's cancel, so it becomes 1/2 C delta V squared. So these are 3 equivalent expressions. This one, and this one. Okay, so depending on which is given, and then not too many people use this, because you rarely get both of this. So it's either this or that, because you don't have to plug it in twice. So that's the relationship here. How are we doing? Can we do dielectrics and finish this really fast? Yeah, because it's short. Dielectric, of course, is the material that you put in between, because you really cannot leave it as an air. They might touch each other and bad things happen. So you have to put an insulator in between, and paper will do. Okay? But if whatever the material you put in molecular level now, you have this, like potentially even water. So this side is more positive and that side is more negative. So it's like molecules are typically polarized, and you put more polarized molecule in here anyway, right? Then they are not polarized in random direction, but once you put charges around, remember that the opposites attract. So these negative charges are attracted by these positives, which will make these things line up. Or the other way of thinking about this, it creates electric field across in that direction, right? And then these molecules, they're not free to move around, they're not conductors, but they all flip and line up. Then effectively, this positive charge is supposed to see this negative charge, but it's really seeing these negative charges. So that gap has been a lot closer. It's not really same as closing it, but it has that effect, right? See, if the electric field is stronger here, then potential difference here is stronger, meaning it's that much harder to pressure these guys in. So these little things line up and creates the field in almost in opposite directions. You know what I'm saying? So that these charges feel as if those are a lot closer to you. Therefore, the effect is reducing that gap. And this is already paper thin, but by putting certain better materials, you can really, really close that gap. Therefore, you increase the capacitance of a capacitor. You want to store more charges in the same space. Okay, so what you have here is delta V. The relationship is you reduce the potential difference between the two by reducing the gap by that much. Okay? Now remember, C is equal to Q over delta V, right? And then Q over, now we are going to put this delta V, kappa, which is the constant of the dielectric. How much do you improve the capacitance, right? So this becomes Q over delta V, and then kappa up here. Good? And that itself, yes.
I'm sorry, I just want to understand, what is kappa?
Oh, this is the amount of the ratio that you improve the capacitance, or amount that this you close the gap. It's exactly not like you're going to take away this whole thing and then that much is the gap. No, it's not really that. It's not that good. But it depends on the material that you put in. So this is like more of an electrical engineering application. And this, if you look at it, that's the capacitance of the original without the dielectric in. So the whole idea is it's just proportional. It improves your capacitance by that much, that factor. And that's what we compare to air or vacuum. You know what I'm saying? So this is the dielectric amount of effect. Okay? Then lastly, I will calculate then how much more charge can you put in by doing this. Remember, C is equal to kappa times delta V with the same voltage. In this case, you can actually reduce the potential difference between the two plates. But if you just keep driving with the same potential maximum of that battery, then, because this is really what counts, how much more charge can you put in, right? So this is same as K C naught delta V, isn't it? Because of this. And then that is kappa, and this whole thing was the original amount of Q. You get it? So whatever you could have put in before, now you multiply that by kappa. Okay, and these are a bunch of, so this is how the most capacitors, they are like cylindrical shape, and the way they make it is almost plate, right? And then you put very thin, paper thin material, dielectric material in between, and you roll it up. So this is like semi-cylindrical that we did, but parallel capacitor, and you can put a lot in it. And then you put a casing around. So most capacitors look like a cylinder for this reason, or you can do it this way, but really it looks like this. Okay, and these are the different kappa values for air being 1, almost 1, and then these are the typical materials that they use for dielectric, and paper is here too. So paper is not really that bad, but silicon oil, oh, whatever that Rex glass is, oh, this is great, right? So this is a favorite material for dielectric. Okay, you can see why water is a bad idea, right? I mean, they have it as a property because water can be polarized quite a bit, so that whatever the material that's easily polarized has give you higher kappa value. How about that? Okay, and that's all I have. Do you have any questions?